Okay, hello, my name is Guillermo Jauregui. We're gonna make the workshop number 6, the frame surface model analysis. This is a continuation from the workshop number 5. You must have completed workshop number 5 to continue with workshop number 6. In this one, we're gonna analyze the frame that we made in the last workshop. So, okay, let's continue. I already have the model open of the last workshop. In this workshop, we have the objectives is to create a finite element model for a intermediately difficult frame system using MCC pattern, performing an analysis of the model and post-process the results from the analysis. The results are looked at 1. Deformation, 2. Von Mises stress fringe, and 3. Marker tensor using two different coordinate systems transformations. Okay, now that we have our model open, we're gonna go to group, create. We're gonna make another group. We're gonna call it FEM surfaces. We're gonna hit apply and cancel. Now we're gonna make the meshing. We're gonna meshing, create, mesh, surface. We're gonna go to quad, paver, quad 4. We're gonna select all of our surface. And we're gonna use the automatic calculation in this time because we're using the student edition, and by using a lower value in global edge length, the chances of our model not being correct is too big. So for being safe, we're gonna use the automatic calculation, and we're gonna hit apply. And we're gonna change our topology to try still paver try 3, and we're gonna leave the automatic calculation. So in the element shape, because this is student edition, the quad one is not gonna be of use because our license will not work with this type of model. So we're gonna use try, and we're gonna select 1 in global edge calculation. We're gonna hit apply. The model is gonna be meshed. Okay. Okay, now we're gonna make an equivalence of our nodes. We're gonna go here still in equivalence, all and tolerance cube. In equivalence tolerance, we're gonna use this one, 0.005, and we're gonna hit apply. Okay, we must change our mesh because we overpass our license. This is the problem that I talked to you later. We're still gonna hit OK. Now we're gonna go to mesh again. You create mesh, surface, still try. We're gonna go with 1.5. Let's see if this works. In the value of the global edge length, seems fine. Okay, we're gonna go to elements. We're still meshing. We're gonna go to equivalence. All intolerance cube. We're gonna hit apply. Okay, still we're under that one. Okay, nice. Surface. Let's see if 2 works. Hit apply. Seems fine. Okay, equivalence. All tolerance cube. Apply. Okay, and seems to be working. Okay, yeah, all nodes are looking. If one is repeated or stuff like that, it's gonna be equivalent. Okay, we're gonna go to verify. Still here, verify element and boundaries. Free edges. We're gonna hit apply. This is how it must look now, since there are no repeated nodes. Okay. We're gonna go ahead and try because we changed that part. Aspect. In the aspect ratio, select 5. Always is already in 5. We're gonna hit apply again. This must look stuff something like this. Okay. Okay, now we're gonna go to group, post, and we're gonna select all surfaces. Okay, we're gonna click in all surfaces, and we're gonna hit apply. The lines are gonna look kind of different. Now we're gonna put on our solid so you can look smooth shaded. And we're gonna create some loads. So we go to load, create force, nodal. We're gonna put our name as dead load. We're gonna go to input data. Okay, this window is not coming. Okay. In forces, we're gonna put 0 space minus 150 space 0. In the forces, we're gonna click OK. And in select application and region, we're gonna choose this top. Okay, this okay. Location and regions, we're gonna choose okay. In select regions, we'll select geometry entities, geometry. We're gonna choose these 2 points, which are the middle one here. This one, this is 0.60, and point number 3. These both points, we're gonna add both. We're gonna click OK and apply, and a force is gonna appear in there. Now we're gonna create other forces, which are gonna be in the backside of the of the model. Okay, we're gonna write a new name, which is dev load 2. Dev load number 2. In input data, we're gonna take this number off. We're gonna put minus 960. We're gonna click OK and go to select application and region. Still select geometry, and we're gonna add these 2 points, which is 80 and okay, 0.37. Both points, we're gonna add them and click apply. Okay, now that we created this load, we're gonna add the operating engine static load, which we're gonna name it as such. Here we're gonna erase this one and write OP static load. We're gonna go to input data, and in the forces we're gonna write minus 100. Ooh, great, to minuses, and again minus 100. Okay, we're gonna write OK and select application regions. And this time we're gonna also choose both of our points, these two, only these ones. Okay, it's kind of tricky. Exactly 0.80 and 0.37 again. I'm gonna click OK and apply. Now the forces are kind of different, kind of like tilted to the side. Okay, now that we done these loads, we're gonna create the load of gravity in this frame. You're gonna go to create here, inertia load, element uniform. We're gonna create the name as such as gravity. You're gonna go to input data. In transaxle, we're gonna write down 0 minus 386.4 in A1, A2, and A3, which is transaxle. You're gonna go OK and apply without selecting an application region. Okay, seems to be some error. Input data. Okay, I missed 1 0. Sorry for that. I'm gonna click OK and apply. I think I'm having a problem here. Input data 0. Okay, I'm gonna write some commas. So okay, that's the stuff. I didn't put a space down there. Then I click OK. Okay, now I apply. Now it's working. Okay, now we're gonna create a constraint from the frame for the frame. Still here in loads, we're gonna create, but now we're gonna here in displacement and nodal. We're gonna fix our frame. So fix frame, fix base. In this case, we're gonna go to input data and translation. Gonna get 0 0 0. I click OK. And we're gonna select our application and region, which are going to be the bottom points is 0.89, 98, 98, 52. I didn't add 98. No. Okay, 98. Add it at 0.1 and 0.90. I think so. Okay. Point. No. Okay, yes, should be 0.90. Okay, 0.90. Okay, add. Okay, and apply. Now we have our constraints in the bottom. Okay, to have a better look of what we're doing, we're gonna to ISO 1. We're gonna go now here to display, loads, BC element props. We're gonna change here in show LBC element prop values, not vectors, only values. This one should be all chosen. Seems right. Okay. We're gonna click apply. Apply and cancel. Okay, now that we've done that, we're gonna go and create our material. We're gonna go to properties, isotropic. In this case, our material is gonna be aluminum. We're gonna add our input properties. In elastic modulus is gonna be 10 E6. In Poisson ratio is gonna be 0.3, and in our density is gonna be 2.61 E minus 4. We're gonna click OK and apply. And now we're gonna define the properties of our structure. You gotta go to here, properties, into the objects, into the properties, sorry. Here we're gonna select shell. We're gonna create a property set name as all frame flange. We're gonna select our input properties, and we're gonna choose our here in mat prop name. We're gonna choose our aluminum, and we're gonna write down a thickness which is 0.75. We're gonna click OK and select application and region. And we're gonna choose, I'm gonna change the view to ISO 1 so we can see. We're gonna choose all the flanges, these parts, the sides. We're gonna select members, and with the cursor we're gonna select only this part which is look like illuminated, only that part. Selected all. I didn't add the other one. We're gonna add top one and the bottom one. Added two. Now that both are added, we're gonna click OK and apply. Now we're gonna still define the properties of frame structure. See here in this part, we're gonna go to input properties. In thickness, we're gonna change it to 0.5. Steel aluminum, the same. We're gonna change the name to, I didn't write this one correct. Oh, it's still the same. Aluminum frame. And this is gonna be the flange, it's gonna be the web. No, okay. And we're gonna select the middle ones, the middle part. We're gonna hit select application and region. Be careful to not choose the flanges. Okay, seems okay. Why didn't I choose? Whoop. Okay, it's not choosing. It's not going. Okay, we seems to have a problem. Okay, we're gonna add it manually. We're gonna rotate. Okay, this seems kind of tedious. Okay, looks like everyone is at it. Yep, every single one is at it. We're gonna click OK and apply. Okay, now that we've done that, we're gonna check if our assignments of loads and BCs are loaded to the case. We're gonna go to loads BCs. We're gonna create load case here and modify. Gonna choose default, and this one is gonna pop up. And you see that all our loads are selected here. Fixed base, that load 2, OP static load, and gravity. I'll select it. I'll do it. Displacement, force, and inertial load. We're gonna click OK and cancel just to get out, just to make sure. Now we're gonna go to group, post, and in this case, we're gonna select all surfaces. We're gonna click apply. No. Okay, yeah. Apply. And so we can see now our meshed model. We're gonna click cancel. And I'm gonna just make this look good. Okay, now, yeah, and center. Okay. Okay, now it's time from the analysis. We're gonna go to analysis, analyze entire model, full run. In solution type, we're gonna select solution parameters. This window is gonna pop up. Request output format. This window is gonna pop up. And we must select XDV. Same, do not move the buffer size, XDV, just click OK. Just check that it's checked. Okay. Be sure that linear static is selected. Now we hit OK everything and apply. Now Nastran is gonna run. We're gonna wait until Nastran stops running so we can continue to look at our results. Okay, now that Nastran has already run, we're gonna go to here in, we're gonna select access results, select the type of attachment is XDV, the one we selected, and result entities. Okay, we're gonna go to select result files. This window is gonna pop up. Select create part 2 XDV. Okay, still here's in available jobs, so just look at it. Okay, and we'll select that one. We're gonna click apply. Now we can go to our results. Okay. Now that we have our results, we can create deformations. We're gonna go to here and create deformation. We're gonna select our this one, the one that we have. This is default A1 static subcase MCC Nastran. We're gonna select displacement translational, sorry. It's just here, constraint displacement translational, sorry. We're gonna select our display attributes. And now we're gonna click on model scale and the scale factor of 0.01. Let's see. And unselect show on the form. Where is okay? Show on the form. I'm gonna click apply. Okay, now it turned white. Yeah, the display shows that the form shape of the structure. It seems like there's not much deformation, but if we look at it this way, there sure is some deformation. It's not linear exactly. We're gonna here go to here again in action, create deformation. We're gonna render the style as shaded, which is render style. Here's one. Okay, wireframe, shaded, and apply, so you can see better, like a solid object. Now we want to see our stresses. So still here in results, we're gonna go to create and fringe. Fringe. Still select here in position not layered, and in okay, magnitude is correct. We're gonna select stress tensor. Where is it? Okay, yeah, here it is. Stress tensor, and the quantity is gonna be in the von Mises, as we said. We're gonna choose a set one. Gonna close. We're gonna click apply, and as we can see, our deformation is mostly in the part that was where the forces were greater, which is in these parts, and with a greater deformation in this part. As you can see, there's a graphic showing the value of the von Mises stress. Okay, now we're gonna reset our graphics. We go to home in this part. It says reset graphics. We're gonna click that one. We're going to go to create, maker, and choose tensor. And now select stress tensor under the select fringe result. Okay, it's already selected, is the only one we have. In non-layered, we gonna select in position at set one, close, and we're gonna check only the XX and YY components, so we must check the other ones, XX and YY only. Okay, now we're gonna go to display attributes, which is in the top. The name's gone. Okay, in display attributes, we're gonna uncheck show max min label and show tensor label. Now we're gonna go to plot options here and coordinate information as if. Where is coordinate? Okay, here as is. Sorry, it is. I'm gonna click apply, and now we can see the stress markers and the results of each one of the stress markers created in the whole model. And if you zoom, you can see each one of the triangles that we made has its own marker of stress and how it works and where is the stress and where it's going and the angle of each stress. You can see each individual one. Okay, I'm just gonna put in the center. Good. Okay, beautiful. Okay, now we're gonna reset the graphics again. We're gonna go to plot options again. Well, still in plot options and coordinate the transformation as global. And we're gonna click apply. Now the only difference between this plot and the previous one is that the coordinate transformation of the global was used to create this plot. This means that the stress components are displayed in the MCC Patron global system. Is just like the one that Patron uses. And that's all. That's the end of our exercise. I hope that you learn and see you in the next workshop.